Okay, so hello everyone. This is Licheng and I'm from University College Dublin. I would like to talk about a full-scale 3D CFD model for the Queensferry crossing with field monitoring data. Because the time limitation, so I will only focus on a domain study. So here is the content of my presentation, beginning with a brief introduction of the Queensferry crossing bridge. And then we'll look at the field monitoring data. After that, I will go through the numerical simulations. And in the end is a conclusion, and we'll have some discussion further. Okay, so wind-induced problem used to be a fatal problem to long-span bridges. Nowadays, we don't hear any bridge failure directly related to the wind effects anymore. But wind effects are still affecting the serviceability of long-span bridges around the whole world. So, well, it is very necessary work to give accurate estimation of wind effects on bridges. Traditional way of doing so is through wind tunnel test, but the method has a lot of limitations, such as the interference of sensors, and to set up facilities are really expensive and so on. So with the rapid development of the computational ability, safety simulations have been introduced to this area, but only for a few decades. And people are still working on to prove that safety method can be a standalone method rather than a complementary approach to internal text. So this is why I'm also believe that the validation and the verification of the safety method is very important. So, and also to date, most safety studies on bridges and aerodynamics are carried out in a skewed 2D model. And only a few number of 3D safety simulations have been undertaken. And to my knowledge, none of the full scale is conducted. So in my study, I'm trying to investigate it and validate a full-scale safety model with the field data. So here, let's have a look of my study object, the Queensferry crossing. So it carries an Amneti motorway which connects the traffic through the first of fours between Edinburgh and Fife in the United Kingdom. It was opened in August 2017. And currently it is the longest 3-tower cable stayed bridges in the world. And it has the highest tower, bridge tower in the UK, and also the longest balanced cantilever in the world. So about the field monitoring system. So Transport Scotland installed a structured health monitoring system on the Queensferry crossing to measure environmental action and bridge actions. So in total, there are 1972 sensors of various types installed over the entire structures. And then there's also an off-site monitoring system installed, which is able to remotely manage the data. In this study, I'm only focused on the anemometers. As you can see in the figure 2, that's how it looks like. So there are 11 ultrasonic anemometers installed on the bridges. Because I'm only modeling the central tower part of the bridge rather than the whole bridge. So the sensor I'm focusing on is it's around the central tower one. There are 5 of them. And as you can see in the figure 3, down there, the point A is the location of the tower top anemometers. point B and point C are on the deck level on each side of the deck. There are also anemometers on each side of the deck. So I will note it at point BW, which means the west side of the deck, and the point BE is the anemometer on the east side, and similar to the point C one. Here you can see a windrows plot of the monthly wind conditions from July to December of 2020. The figure you see here is a sensor data collected from the point A, which is a tower top, because I think the tower top one has the least error from the traffic interference. Here we are mostly interested in the high wind conditions. So from the windrows plot, it can be found that November has the worst wind condition. So I further narrow down the scope and select the 3 periods of time that contains the high-speed wind, and also during that time the wind direction is rather constant. So here in the table, it's the 3 cases I selected. Case A has a main wind direction almost directly from the west direction. Case B had the highest wind speed among the 3 cases, and case C has 30 degrees difference from case A for the wind directions. So it's a it's a large difference of the yaw angles. Then here I showed you the data for the case A directly collected from the anemometers. You can see here the red line is the raw data in every second. So in order to smooth all those sudden fluctuations, the raw data is firstly averaged in 1 minute average value, which is a green line. And then I further processed it as a 5-minute average value, which is a blue line in the figure. So you can see for the blue line, there's no sudden fluctuations at all. And it's very predictable and it's very smooth for the further validation studies. So here we come to the simulations. First is the geometry and the domain. We have 2 kinds of domains here. As you can see in figure 6 up there, it's the most common used rectangular domain. So the green face is the inlet and the red face is the outlet. The geometries over there are set it under the yaw angle accordingly. The inlet and outlet faces were 200 meters and 400 meters away from the bridges, respectively, and the front and back faces were both about 100 meters away from the bridges. So based on these principles, my domain for each cases is created separately in order to save computational power. So you can see for the rectangular domain, so normally there are 2 ways to deal with these yaw angle studies. First one is, as I showed here, to rotate the model or to rotate the domain. But changes in yaw angles of a model like this is quite likely to face issues such as unsuitable domain size or unsuitable refinement region size. And also, you may also have to change the desired data point collection locations. So we have to kind of to recreate everything again, which is quite troublesome. And another common way to deal with this is to apply wind flows from two directions, and the different yaw angle can be achieved by adjusting the relative velocity of the two flows. But this method is quite convenient, but the potential turbulence motion caused by the two flows should not be ignored, in my opinion. So to avoid this kind of troublesome, you can see here in figure 7, a cylinder-like domain is designed. So different yaw angles can be easily achieved by changing the position of the inlet faces. The radius of the domain is 500 meters to ensure that under most of the angles, there are enough space between the geometry and the outline to let the flow fully developed. And you can also see that inlet face is a plane rather than an arc face, just because I want to avoid the interlacement of the incoming flows. And the size of the inlet face is also set it based on the equivalent length of the bridge under the certain yaw angles. Here is the mesh scheme for both domain studies. It's carried out by block mesh and snappy hex mesh. So you can see there are 7 levels of refinement. The largest cubic cells has a depth of 35 meters, and the smallest one has a depth of only 0.273 meters. So the finest cell is placed 1 meters away from geometry surface, and the next level is 20 meters and 36 meters, etc. So I also did a mesh refinement study here, but I won't go detail about that. So here in the figure is what I finally used to the most efficiency one for the further study. Here is how it looks like for the cylinder mesh schemes. So you can see from the top faces, the block mesh cuts the domain in an arc way rather than a straight line. So in my opinion, it's not a best way to generate mesh. So because there is a increasing risk of generating bad meshes in key area, especially when after changing the yaw angles. So I'm trying to figure out, is it possible to cut the domain like in straight line, not in this arc line, but I don't have any idea right now. So I'm glad if someone here can give me some suggestion or tips about that maybe later. Yeah, I would be grateful about that. So here's let's say a summary of the domain conditions. So the most interesting part is the inlet U. So I'm using a utility called time varying mapped fixed value. And this value of the inlet velocity is manually set based on a weather research and forecasting model, which I'll call it WRF model. So yeah, the WRF simulations here is accomplished by Dr. Connor Sweeney, who is also from UCD. So you can see here is a domain of the WRF model. It's a very big model that covers the whole United Kingdom, and the domain grid are 30 kilometers squared, and the height is 3 kilometers. So in figure B, you can actually see the location of the Queensferry crossing bridges, and also the right star point out the Edinburgh airport location, because that's the nearest weather forecast stations for this model to use to to validate, to prove that this model is accurate. Here it is how it looks like. So on the left-hand side, you can see this is a wind profile for my case A. And on the right-hand side is how it looks like in the CFD model, the face of the inlet and how it changes, how the velocity change at here. So also the turbulence kinematic energy and the turbulence dissipation rate will also calculate based on this. So finally here we come to some results. The K omega SST and simple foam is applied for my study. And also in order to create an equivalent environment with field monitoring, so every numerical time step is deemed as a second, and average value of every 60 time step is regarded conceptually equal to the 1 minute average field data, and so on. So finally, we can compare the 5 minutes average field data with the CFD model results. You can see here in figure 10, this is the results for the case A. So the red line is a filtered sensor data, and the green line is the CFD results from rectangular domain. The blue line is the result from cylinder domain. So you can see that cylinder domain have even closer results to the field monitoring data at some point, especially for the point A on the top over there. So overall, the overall average results difference for rectangular domain is 11.7%, and the cylinder domain achieve a 0.2% lower results difference, which is 11.5. And if we look at case C, here you can see on the left-hand side, the results from point BW and point CW, which is a figure B, figure D. So cylinder domain can predict closer results to the field data, which suggests that cylinder domain has a good ability to provide good results as rectangular domains after changing these yaw angles. For these cases, the results difference for the rectangular domain is 7.6%, and the cylinder one is a little bit higher, is 11.2. So when you come to the largest yaw angle among the three cases here, so obviously cylinder domain can still make good estimation, but even though the green line, which is rectangular domain results, can provide better performance at most time. So it shows that after changing a large yaw angles, the cylinder domain didn't show enough robustness. That's maybe caused by the mesh, as I mentioned before. So that's the one I need to further developed. Finally, so here come to the conclusions. So after comparing the two domain results, we can see that the cylinder domain has a good ability to provide velocity estimations as well as the rectangular domains. So both of the domains that results has an average difference lower than 20%, and the maximum difference at each time points is no more than 35%. So this suggests that the cylinder domain could potentially be a very good substitution for the rectangular domains, because it's much convenience, much easier to set up. Basically, that's all for my presentation. Thank you. So I'm glad if you have any questions or suggestions for me. So that's it. Thank you.
Hi there. Can you hear me?
Yeah.
This is Hendrik Hickman speaking. And maybe just a suggestion as you asked for advice on how to treat the bad mesh in terms of the round mesh you had. Have you
Yeah.
thought of using an O-grid for the background mesh? So composing the block mesh of several blocks and then doing an O-grid out of it and then use Snappy Hex mesh on that. Maybe this can help.
Can you go more detail about that? How how does it achieve that?
Do you know what an O-grid is?
I'm not quite familiar with that actually.
Okay, maybe just look it up. It's a specific type of mesh you can use on like pipes and round geometries.
Yeah.
So you get very bad mesh cells in the curved parts. You can find a
Okay.
link
Okay.
and you maybe give it a try. Thanks.
Yeah, I'll look it up later. Thank you. Thank you for this suggestion.
Hello, thank you
Yeah.
for the presentation. I just wonder if you have carried out a mesh density study to conclude the difference that you see between the rectangular and the circular one. It's mainly due to the, let's say, mesh or the topology that you have used.
Sorry, so your question is?
My question is, have you carried out a mesh density study for each of the
Yeah,
topologies
I
that you have?
I did a mesh density study. So right here, I just pick out the final results of the domain study. And the mesh scheme you see here is just it's a results after the mesh density study. Yeah.
Licheng, this is the session chair. I have a question because we have a little extra time and I don't see any in the chat. Maybe I'm being dense, but what about if you had a cylindrical domain or a square domain with equal lengths and you had periodic conditions on two faces and you could just adjust the direction of the inflow velocity and you didn't have to rotate the body or change anything with your geometry. You just change the direction of the inflow. Is there something I'm not understanding that would prevent you from doing that?
Um, my point is that after you changing the geometry, so it's like after rotating, maybe the refinement part will change. So it's not very convenient to do that because you have to change the region of the refinement again. So it's not convenient just because of that. So when I'm using the cylinder one, I don't have to change anything. I can only change the elect face and nothing else need to be changed. So that's it.
Okay, thank you. Say it's an abuse of privilege if I allow myself to begin a minute or so early. Hello, everyone. Again, my name is Dr. Joshua Brinkerhoff. I am the next speaker, and I'll be presenting the work of my master's student, Najiba Akther, who was not able to join us today in a talk entitled Performance Enhancement of Small Wind Turbines via Protective Leading Edge Droops, with a focus especially on mechanisms for transition delay evaluated using large eddy simulations. The context of this work is focused on large offshore wind. Offshore wind is becoming one of the mainstays in decarbonization of energy infrastructure, and the investment in offshore wind projects over the past 2 decades has been leading growth in renewables, and the desire for offshore wind is, of course, due to the higher, steadier mean wind speeds, as well as avoiding visual impacts associated with onshore wind. But offshore wind is particularly troubled by leading edge erosion, which results from debris or moisture damaging the leading edge of the wind turbine airfoil and putting the blade at risk and causing failures or, at best, degraded aerodynamic performance. And there have been efforts to protect the leading edge of wind turbines using a variety of techniques, including gel coats, flexible coatings, leading edge tape, integrated erosion shields, and so forth. In the context of this study, we wanted to evaluate the addition of a leading edge droop in order to protect the airfoil from erosion, and perhaps also to augment the aerodynamic performance of the airfoil. And although erosion is most contextually relevant with offshore wind, which is associated with large turbines, we focused initially on small turbines for a number of reasons. One, smaller turbines undergoing erosion will have their lifespans reduced more quickly and, on a relative sense, more rapidly. Second, the Reynolds numbers for the relevant application for these small-scale turbines is more readily available and more accessible in the context of large eddy simulations. And another reason is because the airfoils with the designed for the small-scale turbines are a little bit less optimized and perhaps more open or more accessible for augmentation of their aerodynamic performance. Today, I will be talking about leading edge droops applied to 2 airfoils, the S822 airfoil, which is an NREL airfoil, and as is used, for example, on Sun Air 100 kilowatt turbine, and the NLF 416 airfoil, which is a laminar flow airfoil, which is used on the Wind Energy Solutions 34100 kilowatt turbine. The motivation here is to address erosion with a passive flow control device that simultaneously improves the airfoil performance. The droop does 2 things, at least 2 things. It lengthens the chord, but we limited the lengthening of the chord to 5%. It also obviously protects the leading edge, and if the droop is made out of a more erodible material, it could be a sacrificial material, or if it's made out of a less erodible material, it could be a more durable alternative. So it could be protection one or the 2 ways. And we wanted to also to investigate the ability of the droop to augment the aerodynamic performance, and this is similar to the leading edge droops that are applied on aircraft during high lift scenarios, for example, takeoff and landing or high altitude landings, etc. And so we designed the droops using a panel method analysis followed by 2D RANS simulations where we saw some of the most optimum shapes for the droop. And then we looked at the effect of those droops on the aerodynamics using a 3-dimensional large eddy simulations. And the reason for doing the 3D simulations will become apparent as I move forward. But it allowed for us to evaluate the anisotropic behavior of the turbulent fluctuations that are occurring on the airfoil and evaluate the effect of the droop on the transition and thereby the aerodynamics of the airfoil for both of these 2 airfoils. So the research outline is as follows. We wanted to develop a knowledge about the existence and the impact of transition on these sub-megawatt scale wind turbine airfoils to verify the findings of the benefits, aerodynamic benefits of the drooped attachments, and then to investigate more detail how these droops affect the aerodynamic performance of these airfoils. And as I mentioned, the approach is to do first a Q-blade boundary element method approach for selecting which droop is optimum for the two airfoils, and then 2D RAN simulations for the specific airfoils that we're looking at, followed by 3D LES. The student who did this work used star CCM for the RANs, and because this is an OpenFOAM talk, I won't talk about those RANs. We'll focus only on the LES, which we did using OpenFOAM. But to start off, let's describe briefly how we selected these droops. We used Q-blade, which is an open source boundary element method solver for wind turbine modeling and design. It simulates horizontal axis wind turbine performance using boundary element momentum method, and it also uses a viscous and viscid panel method called Xfoil integrated within Q-blade to predict the airfoil performance. So what we did is we had a bunch of droops provided to us by our industrial partner, and we added those droops and then looked at the effect of the droops on the airfoil performance and then the overall wind turbine performance. Blade element momentum theory accounts for local blade forces, momentum balance over the rotor disc, and models the flow field. Thrust and torque are obtained from the aerodynamic forces on the cross-section of the roller blade as a function of the tangential and axial induction factors, which are defined in these equations. The F1 and F2 are Pronto correction factors, respectively. And then our sigma, Cn, and Ct are inflow angle, our rotor solidity, the normal and tangential force coefficients. For the large eddy simulation, we used LES, where we filter the Navier-Stokes equations, and then of course we have subgrid models for the unresolved scales. For the LES, we used pisofoam solver, and in that case, the equations are discretized using finite volume method for the incompressible Navier-Stokes, and then mass velocity coupling is accomplished using a pressure implicit splitting operation, piso algorithm, and the continuity and momentum equations are solved twice. The pressure equation is solved twice in the piso loop, and then with each corrector, we solve the pressure matrix 4 times altogether. The subgrid scales are resolved modeled using a dynamic K equation, which is fairly standard. The formulation is presented on the slide. We set up and ran the simulations on 384 processors of a cluster, and we monitored the lift and drag coefficients for the airfoil section until we saw the flow reaches a statistically steady state, and then we begin averaging over a period that corresponds to at least 3 or 4 flow-through times, which corresponds to several hundred cycles of the periodic vortex shedding and transition processes that occur on the airfoil. Here are the results of our droop selection exercise, which we did in BEM. The different lines correspond to different droop shapes that we used on the right-hand side, and on the left-hand side is the glide ratio, or the ratio of lift and drag coefficients as a function of angle of attack for all the different droops, and then the solid black line corresponds to the base airfoil without any droop attached to it. And we can see that the different droops have various shapes and various aerodynamic impacts. The best one is labeled D1, it's the solid red line, and what we see is a 30% increase in the glide slope ratio, which means it's augmenting the aerodynamic performance quite appreciably. The NLF airfoil is a little harder to improve. It's already a fairly well-performing airfoil, but we still do see a slight increase in the glide slope, in the glide ratio, where we got a 4% change with droop number 23, which is the solid red line again. Now we want to evaluate these droops in LES to verify how the aerodynamic performance is changed. For both, we conduct the LES at a Reynolds number of 500,000. The airfoil incidence angle is chosen to match with experimental data that's obtained. which means it's a different angle for the two different airfoils. It's 11.19 degrees for the S-series airfoil and 10.18 degrees for the NLF airfoil. The reference velocity is 1. The time step size is selected such that the current number constraint is satisfied, which automatically then guarantees that we have the correct time step for resolving the turbulence scales. Our boundary conditions are imposed with a free stream velocity. We use cyclic top and bottom boundaries because the airflow is coming in with some angle of attack. And there's information about our grid. The total number of cells is about 46.5 million. We did do quite an extensive grid dependence analysis where we varied each one of these numbers independently for the number of cells in the curvilinear directions that are aligned with the chord, normal to the chord, across the span, in the wake, along the foil, etc. Here's a view of the time averaged flow field. This is in terms of the pressure distribution for the S822 airfoil. The solid lines, the dashed black line is the prediction from X-foil. Regrettably, the experiment only provided lift and drag coefficients, not the CP distribution. So we're comparing against X-foil as the reference. Whether it's more true to real life or the LES is more true to real life, no one can know. We don't have the experiments. But in terms of the match with respect to experiments for the lift and drag coefficients, our LES results for the non-drooped airfoil agreed to within 1.5% or 1.4% for the lift and drag, respectively, corresponded to the published results from NREL. When we add the droop, so the red is the non-drooped case, the blue is the drooped case, a couple of things happen. First of all, we have a much more mild suction peak. So this suction peak that occurs on the suction surface is not nearly as abrupt. It's spread out over a longer chord-wise distance. Obviously, the droop extends the chord a small amount, around 4%. And as a result, there's a much lower amount of flow acceleration and deceleration over this milder portion of the airfoil, which we'll see has a significant impact on the transition process. Let's zoom in on that a little bit. What we see in the red, the non-drooped case, is a leading edge separation bubble that occurs at this Reynolds number, and we can find the location of the separation and reattachment in the time mean flow, but we don't see such a leading edge separation bubble in the drooped case, which is the blue. That is to say, so here we have isocontours of the Q criterion and colored by the velocity magnitude. The top one is the non-drooped base airfoil, and when we look at the transition process, we see that that leading edge separation bubble, which is colored red, initially has relatively span-wise homogeneous disturbances being shed from the separation bubble. We think that that corresponds to an inviscid instability like a Kelvin-Helmholtz mode, which very quickly rolls up and becomes three-dimensional, and the amplification of disturbances in that laminar separation is quite strong, and thereby we have a rapid transition to turbulence that then continues and evolves as those structures begin to interact with one another and grow to a more fully developed turbulent boundary layer over the rest of the airfoil. On the drooped airfoil, because we've significantly reduced the strength of the adverse pressure gradient, we do not have a laminar separation bubble, and as a result, the disturbances that evolve near the leading edge occur much more gradually. We don't have, the transition process is more gradual. We still see an amplification of disturbances, but they don't begin to saturate, the inviscid mode doesn't begin to saturate until around 20% chord. After which we do see these span-wise structures being shed. They shed downstream. There's some interaction. They live longer in terms of there's more periods of those. They begin to break down into three-dimensional structures and then continue to evolve. And by around 60 or 70% chord, the turbulence is similarly developed. But we have this 20% chord at the very leading edge where the transition is delayed, and the rate at which the transition onset location is delayed, and the rate at which transition progresses is also delayed. And this is a significant impact on the droop. Okay, so just to summarize what we saw in the videos, these again show instantaneous isosurfaces of Q criterion, don't know why it says O criterion, it should be Q, where we see again, just to summarize, the base airfoil undergoing a abrupt laminar to turbulent transition near the leading edge due to a amplification of a inviscid mode where the boundary layer separates, rolls up into into span-wise coherent structures. Those interact and break down into three-dimensional structures very rapidly, reattach as a turbulent boundary layer, and these hairpin vortices evolve and grow in the flow as it flows over the rest of the airfoil. In the drooped case, that laminar separation bubble is removed. Amplification is significantly more delayed. There is a disturbance amplification, but it's not until much later on that it begins to form these similar type of attached turbulent boundary layer with hairpin structures evolving, and you have this turbulence production cascade regeneration of these hairpin structures. All right, the same thing viewed from the top. I won't comment more other than we can see really clearly here the shift in transition onset location and how much more rapidly transition progresses in the base airfoil. This is a visualization of the instantaneous vorticity on the surface, if you like. It can be a proxy to the skin friction coefficient. And what we see is that in the base airfoil condition, the breakdown to turbulence results in these non-coherent turbulent streaks that are significantly aligned in the chord-wise direction. Those evolve and stretch, and then by around 60 or 70% chord, break down into more small-scale turbulent structures. Whereas on the drooped case, we see a relatively gradual boundary layer separation. So it does occur, it just occurs way more gradually. Then we see much more significant span-wise coherence over a long period from about 25 to 40% chord or 45% chord, and that span-wise coherence doesn't go away until maybe even around 80 or 90% chord. So the amplification of disturbance is much more gradual, and it maintains the memory of the 2D inviscid instability, or at least the 2D instability for much longer, where we see these span-wise coherence in the turbulent streaks and their impression on the skin friction. This is the time mean look at the separation near the leading edge for the base airfoil, where we show the separation location, the reattachment location, the imprint of the separation bubble on the skin friction. And then we look at unsteady and dynamic reattachment. This again is the surface skin friction coefficient, where we see that the separation is very unstable and it falls apart very quickly. And then on the bottom right, this side, is the amplitude of the streamwise velocity fluctuation. So if you like, these are Reynolds stresses, and we see two peaks. One is much more dominant, the outer mode, although there is a much less dominant inner mode. The inner mode corresponds to viscous Tolman-Schlichting instability that's progressing but gets significantly overpowered by an outer mode that exists near the edge of the boundary layer, and that's attributed to an inviscid Kelvin-Helmholtz type instability of the separated shear layer. In the drooped case, the same Reynolds stresses only show one mode, and it's nearer to the ground, it's nearer to the wall. It's not near the edge of the boundary layer, and it occurs much later. So what we think we see is that this inviscid mode that was triggered in the non-drooped case is being not triggered in the drooped case, and instead the drooped case is triggering viscous instability, and that leads to the growth of disturbances and then eventual transition. It does separate, but the separation is extremely mild in the drooped case, and it occurs much later, nearer to where the before where the transition really occurs. So the separation is probably not dominant in driving transition in the drooped case. So again, the droop significantly relaxes the section peak on the leading edge. It's protecting the leading edge from erosion, it delays transition, and it improves quite significantly aerodynamic performance overall. This is visible as well when we look at the Reynolds stresses contours in log scale on the base and drooped airfoil. We see the high streamwise Reynolds stress over the whole airfoil in the baseline case, the non-drooped case, whereas in the drooped case, it only begins to amplify at around 20% chord or so. All right, We can talk more about the disturbance amplification, the different mechanisms. We attribute one mechanism to another by looking at the power spectral density of the instantaneous streamwise velocity for the baseline case on the left-hand side and for the drooped case on the right-hand side. In this case, both of these are being looked at the identical locations. And what we see in the non-drooped case at 2% chord, there's really no power whatsoever. Whereas in the drooped case, we can see a peak at the shedding frequency that corresponds to the Kelvin-Helmholtz. And we see that there's a certain peak that peaks near to around 3 to 6 displacement thicknesses from the wall, right where the shear layer instability is being triggered. And that's not present in the drooped case. Again, evidence that the drooped case is avoiding the triggering of this inviscid instability. However, if we looked at the drooped case further downstream at 16% chord, we still do see that inviscid mode that's present. It pops up, but it's not nearly as amplified and it doesn't trigger the transition in such a strong way as in the drooped, non-drooped case. The final comment here is that around 30% chord, we get a very small portion of inertial decay that follows Kolmogorov's 5/3 law, this right here. This is a small portion of it. And one could argue that that's an indication of excessive dissipation in our numerical scheme. That's possible the case, but I think it's more likely that the flow hasn't a chance to develop inertial scales yet because it's transitioning and the turbulence is still developing as it flows over the airfoil. By 30% chord, it's barely reached what we would consider a fully turbulent boundary layer. Now let's focus on the other airfoil that we looked at, which is a natural laminar airfoil. In the laminar airfoil, they're designed to have as much of the leading edge already be laminar. So the non-drooped case at the very top shows again what we saw. It's a delay of transition. In this case, it's the base airfoil itself. It has a relatively gradual transition process. And the transition process, it's a little bit, these animations are a little bit blocky, but what we see is again an amplification of disturbances that result in a streamwise grouping of spanwise vorticity that then interact, produce hairpin structures that undergo mutual stretching and tilting operation, fall apart into three-dimensional structures, and then form these hairpin vortices as they evolve over the airfoil. And what does the droop do? Not a whole lot. The airfoil already is a relatively well-performing airfoil. It's designed to avoid or have delayed a transition. Adding on the droop doesn't really change things tremendously. So this provides an interesting counterpoint to the S-series airfoil, where we saw the droop really change things a lot, and it really significantly impacted the way that transition happens. On the NLF airfoil, less so. So if we look at where transition occurs, we see that it is slightly delayed, but only by a few % of the chord, and the breakdown to turbulence is quite similar for this NLF airfoil. The same thing is visible in the surface instantaneous vorticity, where we see spanwise non-coherent turbulent streaks. The droop and the base case have very similar locations where these turbulent imprint of the turbulent vortical structures on the surface are evident, and the spanwise non-coherence is occurring. The other thing that we notice is the breakdown to small scales is delayed. We don't even see it on the NLF airfoil, whereas you could see it much more clearly on the S-series. Again, this shows how the NLF airfoil is really designed to be natural laminar flow. That's what the NLF stands for. Okay, again, the same comments about the impact of transition on the leading edge friction factor, the presence of inflection points or the absence of inflection points leading to the triggering of inviscid modes. I don't have time to really look at this, so maybe we'll again focus on the Reynolds stress distribution. Again, the base and the drooped airfoil not being tremendously different in the context of this NLF series. And this brings me to the end. So to summarize, in our S-series airfoils, attaching a droop significantly augmented the aerodynamic performance by delaying the leading edge transition, delaying and removing the leading edge separation and the unsteady dynamic reattachment, so that the breakdown to turbulence is delayed and the growth of three-dimensional vortical structures in the turbulent flow is also delayed. The spanwise turbulent streaks are found after transition in all cases, but the uniform span-wise coherence is observed to be present for the drooped SA22 airfoil. And so the droop, again, delays the creation of small-scale 3D structures in the boundary layer. The aerodynamic gain, 2% increase in lift, 9% reduction in drag, attributed by the droop to the S-series airfoil is the result of this delay in laminar to turbulent transition. The laminar airfoil experienced transition via cage instability with and without the droop. The droop didn't really change anything too much on the laminar flow airfoil as compared to the S-series airfoil, which was significantly impacted. Thank you again for your attention. I'm welcome to receive any questions. This point's a bit awkward. I'm going to try to answer questions and also coordinate the asking of the questions. So if there are any questions, yes.
Thank you so much. Just one quick question and one big question. What is the boundary condition at the sides of your boundary layer, sides of your domain? And the other one is that what is the, have you seen or have you thought about any criterion that defines this method is useful for such kind of airfoils or is not useful for such kind?
The answer to the first question is the span-wise side boundaries are periodic, and the chord, the span, is 25% chord. And we played around with one full chord span and 10% chord, 10% and 25% didn't have any change. So we went with the slightly larger one, but not all the way to one span to avoid the cost. Then the second question, what can we do to know when a droop is going to be helpful or not? And the answer is the BEM. The low-cost BEM method was very close to the LES in predicting how much impact the droop will give, but what it couldn't answer is why. The LES provided the why, and so now that we have a pretty good sense as to the BEM being able, very, very fast, seconds gives us the answer, and it's physically explainable in the context of the LES, which took like a year to do, then that gives us some confidence in the BEM being a useful predictive tool, not something that I would put onto a turbine without doing some wind tunnel experiments, but at least gave us some direction as to why the BEM is giving us the predictions that we saw.
10, your angle of attack was about 10 and 11, right? It's for S-series, it's usually the beginning of this separation. I don't know about the other one. Have you ever thought about the effects of this technique on high angle of attacks, or have you done such simulation for high angle of attacks, or if they're going to help us for the flow control or separation reduction?
So the problem with the droop is it's fixed, right? So if we wanted to put it on there and then change the angle of attack, it's not going to be optimum. So we targeted the droop to work at the angle of attack where CL over CD is maximum. I'm not sure if I would put a droop on if the only thing I wanted to do was like to delay transition or to augment the high angle of attack operation. Maybe there's smarter ways of doing it using active methods. But the droop is useful in that it solves, or at least it helps to address the erosion problem, and it doesn't make the airfoil perform worse. In these cases, it was a bit better. In the large turbine simulations, DTU and like more than 1 megawatt scale, it didn't make as much of an improvement, but it didn't degrade the performance either, so it was not a bad thing. Other questions?
Yes. Have you considered roughness on the droop as well? How do you can incorporate roughness with LES? Any idea on that?
I'll let my graduate student worry about it. That would be a hard one. Probably we'll use an immersed boundary method. We have a very sophisticated one in my team that we've developed. But it's a very important question, especially since the droop is supposed to be eroded.
Thank you for the talk. Have you considered, if you do a blade resolve, like full simulation with rotating blades, the three-dimensional effects and the span-wise gradients might affect your transition point?
Yeah, we know that those will be important, but we haven't looked at them yet. Yes. Although the BEM does account for those in the reduced order model, the LES doesn't. But the LES motivation was to explain why we were getting better than predicted performance with the droop on the in the BEM. We were pleasantly surprised with how well it worked, and we didn't want to believe it until we had some better fidelity model.
Yeah, thank you. So, hello guys. So my name is Rathan. I'm a PhD candidate of UPC. So my topic is on investigation of diurnal cycle of slope flows in mountain valley regions using OpenFOAM. So let me introduce the diurnal effect. So basically, it occurs because of the temperature gradient, which is happening between the surface and the air. So during the day, we have the upflow, like let's say if we take a mountain region. So, and during night, it has the downslope flow, and we call it as a katabatic flow, which is for the downslope, and for the upflow, which is anabatic. And basically, the temperature gradient is responsible for the diurnal effect. And if we take the weak synoptic wind conditions, so these thermal winds are very responsible to have these diurnal effect in mountain valley regions. So the motivation for my problem is, so basically these katabatic and anabatic winds, so they are very responsible for exchanging the flow between the upper layers of atmosphere. So let's say the katabatic flow will bring down the pollutants, and the research has been shown that, so it has reported a wind speeds of 10 to 20 meter per second in the Antarctica region, so which is of katabatic study. And there is a possibility of placing wind turbines or any other alternate source of wind energy in these regions, so we can get an additional wind resource and if the synaptic wind conditions are not okay. So literature studies have shown that, like Stevenson, like he had simulated with the LES conditions, and Barkons had simulated the same diurnal effect with the URANS model, so which is of ALIA CFD wind code. So basically, this is from Barcelona supercomputing. So these models have been taken on the realistic conditions. Now, uh, what I am looking for is whether OpenFOAM can predict the atmospheric boundary problems accurately or not. So it's like the ventilation. So let me give an example of ABL flow. It's like ventilating cities and flow over mountain valley regions. And we have, let's say, like wind turbine things. So basically, whether these things it is able to predict it properly or not, so that is my study. So in my problem, so basically I have chosen a mountain valley region, so which is of 20-degree slope. So this is an idealized structure which is of an example of ventilating city of Tokyo in Japan and other Phoenix in US. So this is my problem. And one other thing, whether I'm able to simulate the diurnal effect using OpenFOAM or not. So this has to be checked. So this is being seen in the study. So as I stated, the Barkons, so he has given a 5 cycle analysis actually. So let's say 0 to 24 is a cycle. So he has done for the 5 cycles, and he has taken the surface temperature, which is varying with respect to time. So cyclically, so here you can see the 5 cycles thing, and he had given the temperature boundary condition where it increases and decreases. And here it is observed that during the day, so an unstable atmospheric boundary layer has been developed, like unstable flow, and during the night it is thermally stable. So in these conditions, he had given a geostrophic wind which is of 9.5 meter per second. So, and he has considered an location from Mexico, which is Pueblo Mountains. And here you can see the simulation results that he has taken different stations, which is of 4 stations. And with respect to geostrophic wind velocity, so you can see that it is obtaining the diurnal effect. So the velocity which is varying, let's say it is from zero, again it increases, again decreases. So the effect is being observed with the URANS, which is unsteady Reynolds average Navier-Stokes equation, with the Allia code. So the main hypothesis of my simulation is that there is no synoptic wind condition. So it means like I haven't considered any initial velocity. So the temperature gradient drives the boundary layer. So it's like the flow propagates or the flow convex because of temperature gradient between the mountain, which of between the slope and the field. And I have taken the Boson's approximation. So then the fluid which I have taken Newtonian perfect gas, and the flow solver which I have taken turbulent incompressible flow, and they have taken only conduction and convection phenomena. So I haven't considered the radiation effects on the slope, and the Coriolis force have been negligible. So before that, literature studies have shown that K epsilon, RNG K epsilon model and K omega SST model. So these can be basically used for the simulating atmospheric bound layer problems. So I have considered a 3D domain. So from the literature, which is of Schumann and Axelson's. So basically, Schumann, like he has the domain which is of 10-degree angle slope, and he has simulated with the LES model. So basically this is of second order accuracy, and Axelson basically he had validated the Schumann's results and shown an improvement with the sixth order accuracy schemes. Now I have taken the geometry and seen, so with the RANS model, so which is of Reynolds Navier-Stokes equation, so which is of K epsilon and RNG K epsilon and K omega. So here you can see that out of three, so the K epsilon model is able to reach a steady state, and here you can see the RNG and K omega. So basically, with respect to time, so you can see the deviations. From these things, like you can see that the K omega SST model uh, can't be seen. Why? Because like you can see with respect to the non-dimensional height, so they near to the boundary, so there is a lot of uh, wiggles which is occurred for the K omega model. So by eliminating the K omega model, now we have like K epsilon and like RNG K epsilon. So I just want to check again whether the RNG K epsilon model will work efficiently or not when compared with the K epsilon model. So what I have considered is the two simulations, like with different boundary conditions on the top surface of the domain. So basically, uh, on the top surface, a slip wall boundary condition has been used, and a symmetry boundary condition has been used. So basically, here uh, the thing is that if we use symmetry boundary condition, whether it is able to predict properly or not, it is one check. So it has been seen that symmetry boundary condition has been given an error of approximately some 24% when it is compared with Axelson, so which is of sixth order accurate scheme. Uh, and when a top wall slip wall boundary condition has been used, so there is an error of 4% when we compare with the Axelsons, and 7.8% when with the humans. So with this, I just concluded that so a slip wall boundary condition on the top surface can be used, and K epsilon turbulence model is to be used to simulate the atmospheric bound layer problem. And for my problem, I chosen a K epsilon model and a slip wall boundary condition on top surface. And coming to the mesh of my the domain, so here on the left you can see so this configuration is an idealized configuration, as I told you, idealized configuration of a mountain and the streets of the cities. So basically here in the flat surface there will be some streets, but here I didn't use those streets. Basically, I just kept flat surface. So idealized location of the Tokyo in Japan, as I told you, Phoenix in US. So this structure of 20 degree slope angle is taken from that, and here you can see on the slope. Basically, I have used a no slip uh, wall boundary condition, and on the left and the right surface I have used the symmetry boundary conditions, and on the flat surface again no slip boundary condition is used, and on the top surface a slip wall boundary condition is used, and in the internal field I have taken 288.15 Kelvin, and there is no initial velocity, and on the mountain slope, a sinusoidal temperature boundary condition is be given such that so after 12 hours the temperature let's say it is decreasing from 288.15 till 278.15, again it start picking up to 288.15 and goes to 298.15. So it is a sinusoidal wave kind of condition. So the domain height studies, what I had, domain height, domain width. So these studies have been already done in my previous studies. So with that, so a domain height of 3022 meters was sufficient, and 458 meters was sufficient to see that there is no effect of the domain on the mountains, on the values of the mountain slope. So the simulation setup, coming to the simulation setup, so I've considered a transient solver, so which is a buoyant bosonic pimple form solver. So here the time scheme, so basically initially I started with the robust scheme, which is of Euler first order scheme, such that if there are any wiggles or if there are any oscillations in the uh, simulation, so those will be taken care of once it obtains a stable mode. Then I switch to the second order, which is of Crank-Michelson scheme. Then the gradient and the diffusion terms have been taken as Gauss linear, and the convection terms has been taken as Gauss upwind and linear. So, and coming to the wall functions which I have, so basically the K epsilon model which I have taken has like turbulent viscosity, turbulent kinetic energy, and dissipation rate, and the diffusivity. So these are the wall functions which I have taken. So these are taken basically from the studies of the OpenFOAM website which we had. So I studied with the wall functions and chosen these are the useful things for my study. Uh, Once the values which have been shown, so these have been calculated from the standard equations which with respect to the roughness. coming to the results, so basically I've been simulated like for the three cases. Here you can see the simulation setup has been run with a time step of 0.125 seconds and 0.25 seconds and 0.5 seconds. So these are the three cases which I have. Now the mesh size which I have like is 0.09 meter, so which is of the which is the first cell which is, or the first grid point which is located above the wall. Uh, so that value has been come from the mesh independent study, and this been already discussed in my previous work. Now with that mesh configuration, now I've been checking, so these time steps such that these things lie in the current number in between the 0.1 to 0.9 actually. So these studies has shown that uh, the all the three cases are able to produce the cyclic nature. So that means like, so if the velocity, let's say it is starting from zero, is able to go to the max and go to the min and able to come to the original. So but here you can see the oscillations. So this is because like this is only of the two cycles. Okay, so this is of the two cycles which is being studied. So now if you see the left, middle and the right pictures, so the left one is the upper point, that means the location at x is equal to 171.75 meters, which is at the y of 437.5 meters. At that location, I have calculated the value of umax with respect to time, and it has been found that a maximum velocity of 3.5 meter per second is obtained for a delta t of zero point 0.5, and for 0.25 it is of approximately 3.8. And now you can see for the delta t of 0.125 it is of nearly 4.1. uh, Here at different locations you can see that the velocity umax is not uniform, since for the for the anabatic flow, the boundary layer, uh, the upslope flow which propagates to the top of the mountain, like which has the highest velocity at the upper point, and for the katabatic flow you can see uh, we have at the lower point the umax, and at the middle, like you can see it is of the average of the upper and the lower. And here uh, this is the contour which is shown for the anabatic and katabatic flow. So here on the top you can see that this velocity profile is drawn at that 171 point at the upper point location, and here the corresponding vector plot is shown, and you can see that this has a similar profile, so which is like a which has been simulated with the other codes, and during my uh, PhD uh, research proposal defense, there was been questions asked from the other departments. So we have other models to predict these atmospheric boundary layer flow problems, it's like WRF, and there are other codes which are extensively used to predict the weather conditions and these things. Why only OpenFOAM? Like people have asked me, and during that proposal kind of things, so there were many questions being raised. But these velocity profiles and the results which have been shown has gave some confidence to them that yes, OpenFOAM can able to simulate the atmospheric boundary for problems, and it can produce the diurnal effect. And it in the future, like we need to see whether like it can produce a realistic uh, it can reproduce a realistic condition values, or let's say when I place a realistic topographical regions, so how complex it is and what is the computational cost, and these things has to be investigated for my future simulations. So thank you. So I'm open for the questions.
Thank you, Rathan. Are there questions on the floor? Okay, I see some questions.
Hello, thank you for your presentation. I just got two different questions. The first one is about how would you start with a different zero velocity? Could you take, for example, like the average velocity of the mountain to differ from that start point? And the second question is, what is the main uh, importance of such modeling? Because if we are talking about placing wind turbines, can we place it on the top of the mountain or in the lower part? So why do we need like to model the variation of the temperature along the mountain?
Yeah. So for the first question, like basically the wind turbines work with the synoptic winds. So now, why there is no average velocity being taken as is like, so how much amount of maximum velocity that is being generated with pure temperature difference between the mountain and internal field has to be seen. So that's why I haven't considered any average velocity in the initial condition. And the second one, so yeah, for the future work, like basically there has to be an optimal location to be verified where we can place the wind turbines uh, to extract the energy. It's a initial work which I've been doing. So my work is to see uh, at what locations or at what point like we have the maximum velocity on the mountainous regions with only pure temperature differences. There is no synoptic wind, or let's say there is no external wind which is coming from the pressure gradient. So that is my motivation.
Other questions on the floor? Rathan, I have a question. When you showed one of the slides that showed the wind that goes up, I forget what it's called, catatonic, I think, or maybe
No,
anabatic.
anabatic actually.
Thank you.
Yeah.
I'm going to be catatonic after I'm done this. Um,
Yeah.
that one, when we looked at it, goes up, it gets to the top of the mountain, then it keeps on going up, and then it looks like it recirculates on the top because of your top boundary condition. Is that artificial? Is that a problem?
It didn't affect any affect any thing on the mountain slope, so it didn't reflect any flow on the slope. The basic thing is like the flow on the mountain on the top surface will just touch and move tangentially. So there is no outflow on the top surface. We didn't just kept. So in the literature studies, people had used some artificial, some damping effects to see that the flow is being straightened actually. So instead of keeping the outflow, we just use the slip wall boundary condition on the top surface. And when it is forming the vertex, let's say from the peak of the mountain and flowing all over the top surface, so it didn't affect anything on the slope actually.
Okay, but how can you be sure that that vortex that's there won't have an impact, or are you really confident?
We had seen like the effect of height domain height study. During the domain height study, so I started it from 1400 meters till 3800 meters of domain height study. So when I had taken a domain height of 1400, it has impacted actually. So it has impacted. So let's say the domain height of 3,200 meters, in the sense it's almost 3 kilometers. So the flow which is of 3 kilometers of, let's say, the height of the domain, it's like 3 kilometers. So the velocity what I have on the, let's say, on the top surface is of 3.5 meters. So there by the time it comes and affects to the mountain slope, it again mixes with the other flow which is of the which is present in internal fluid. So yeah, basic thing is like we had seen the variation of different domain heights, and as you asked, it has impacted for 1400 meters of the domain, 2000 meters and 2600. So when we had varied for other domain, let's say 3200 and 3800, it didn't affect on the slope. So with that we had concluded that okay, this configuration will be helpful to study the slope flows.